Okay, maybe we'll get started then. So this week we have Beau Paisley from ARM again, giving us the second of his talks, this time about optimization using map and performance reports. So take it away, Beau.
Great, thank you. So kind of the agenda today is just a brief PowerPoint presentation overview of the tools, very similar, pretty much the same as I did last week. So for folks who were last week, sorry about the redundancy, but I do want to focus on the slides about performance methodology. It's really important about what we're going through, and then we'll go through a hands-on demonstration of creating a performance report and analyzing that, creating map files and analyzing those also. So Forge is the integration of our debugger, DDT, our source code profiler map, and our application profiler performance reports. The tools are really focused and designed from the ground up, both user interface and architecture-wise, to be optimized for HPC applications, in particular SPMD style applications that might typically use MPI and OpenMP tools. Especially in our performance tools, really focused on ease of use, so anybody can pick them up. There's a lot of good performance tools out. I'm not really familiar with your site, but I'm sure you have some of the other alternatives, and there's really a range of focus in performance tools. There's really high power tools that enable instrumentation and looking at very low level details. Our focus with our performance tools is really large scalability and ease of use for any type of end user. Someone that might be a domain scientist, not necessarily a computational expert, and also very efficient and safe, so to speak, when running at scale. I know plenty of times in my career I'd have situations of I've instrumented a code and I'm running at pretty good scale, and before I know it, I overrun the file system. And it's very easy to do with some of the high power tools, and our sampling technique really helps keep the tools safe, so to speak, from overrunning your system. So just kind of an architectural overview of Forge, and we'll go through the interface a bit today. Same interface we were using with DDT, but accessing through the performance tools. DDT highlights, I won't go into this detail. We went through a demonstration of all these last week, but I like to keep this included in our overview slide. Now, the performance roadmap, I did present this last week, but I really want to go into this depth this week, and I'm going to reference this quite a bit today when we're going through kind of methodology. It's really important when we're optimizing codes to kind of really follow a process and follow in the correct order of what we need to do. I've had a lot of opportunities to work with customers helping on their actual codes of improving things, and it's often interesting to say, oh, I think I can improve the vectorization, and people want to like dive right into CPU related things or memory related things, which are important, but especially on HPC codes, it's really important to look at the potentially large problems first. So for example, in I/O, we can lose orders of magnitude of performance if something is really set up wrong. So in the performance roadmap, and I like to go through this, number one always is program correctness. So really important as you're making performance improvements to frequently run your regression tests and make sure that you haven't introduced any bugs. Because if you make a whole bunch of optimizations and all of a sudden you realize, and there's some bugs that have been introduced, you might have to roll back quite a few versions and quite a few steps before you find what's wrong. So really run your regression tests frequently. Most large codes, you'll have a built-in regression test. DDT can also help you with that. Analyzing the performance before you really decide what to do. We'll be looking at both of our tools today, performance reports and map. I really encourage as a first step to look at performance reports because it's a high-level view, very easy to understand. You can get the output without symbols in your code, just a general release build. And then moving through, I won't go through a description of all these, but essentially the order of operations of kind of largest potential problems to least potential problems. It's typically I/O, MPI related workload balance problems, memory access patterns, and then kind of on the right side, getting into actual CPU utilization. Also, one thing I wanted to mention on this, I didn't really say in the overview, but I find it's kind of important to highlight now, is we support all the major architectures. Being part of ARM now, folks often ask, well, do you only work on ARM processors? Obviously, ARM processors are a priority for us, and we certainly work on ARM processors, but we also support x86 processors and power processors also. We have a few US government labs using power architectures. And we also support NVIDIA GPUs, and I'll talk a little bit about the NVIDIA GPUs when we get into demonstrations. Okay, so I mentioned performance reports as a tool for kind of the first step in the analysis of your output. So this is just a sample, and we'll actually create one and look at the details, but it's a single page HTML report. At a high level, shows you time spent in compute. If you're using a GPU, it'd break that down into both time on the device and time on the host, time spent in MPI and time spent in I/O, and then a little bit of breakdown below that. And one thing we can do in performance reports, which we can't really do in a source code profiler, is from kind of the shape of these different bar charts, we can apply some heuristics and give some kind of subjective advice of what might be improved. So for like example, a classic one we often see is running at a given scale where you're using a relatively small percentage of the memory on the node. It's often the case if you're doing that, there might be opportunity to actually use fewer nodes with more compute and memory usage per node, some of those type of things. Or if there's a bit of time spent in collectives in MPI, it'll flag that you have a lot of processes that are not doing their share of work, so to speak. Very low overhead. Both map and performance report, we aim to have below 5% runtime overhead. It's actually quite a bit less usually with performance report. As I mentioned, don't need symbols, just run at your usual optimization level. And that's an important thing to highlight also, by the way, is for all of your performance tuning, you want to run at your release level of optimization. The compilers do so much improvement, factoring of code, that if you don't run at your release level of optimization, it's really not very meaningful, and you're probably going to be looking at the wrong things. So map. So map is our source code profiler. Just to highlight what I feel are some of our greatest strengths and most important capabilities. And we'll go into many of these today in a hands-on. Looking at memory usage. So in the tool, we'll give kind of a chart of how memory usage changes in time, a very useful way to see that you're getting good utilization of the memory. And it's also a good debugging tool. I mentioned when we were in DDT last week, the tools in DDT for looking at memory usage. One technique that I've been promoting in recent history is using the profiler also as a tool to see memory leaks. So you'll see a chart, and if you see a jump in memory usage, you can drill down and see where in the source code that jump is occurring. And if that's not something that you expect, it's often a quick way to isolate in the source code where a memory leak or ill behaviors are happening, and then go back to DDT and use the memory stats and memory usage tools that we talked about last week. MPI imbalance, this one's really key. Once again, one of the first steps on the performance roadmap is looking for cases where you're not distributing the work across the processes as well as you can. And we're going to go through an example of that one explicitly also. Very similar for I/O. I/O can be even worse of easy to have deadlock and bottleneck situations where you're not using the utilization well. And actually in my follow-up notes, I have a reference to a blog where we go through refactoring the I/O of an application from kind of a raw I/O system to use HDF, which can greatly improve that and increase balance. Analyzing OpenMP, similar to looking at balance of computation across MPI, but across processes. is seeing that you're getting a good workload balance of OpenMP and using using all the threads well. Memory access patterns. Map is very visual, very easy to see how you're accessing memory and getting good distribution. And then kind of the final milestone on the roadmap, so to speak, is vectorization. And this is continuing to be important and more important. I'm seeing a lot more customers going between architectures. Obviously, being part of ARM, we're seeing a lot of folks that are picking up ARM processors coming from x86. And for the most part, that's pretty simple. Most codes compile and run, pass the regression tests, and usually have decent performance, but oftentimes it does require going in and looking at vectorization, as that is done a lot differently on ARM than it is done on x86. So just a screenshot and kind of a highlight view of map. So very visual oriented, and we'll go through an interactive of looking at this, but I want to talk a little bit about the architecture of how we gather data. So map is a sampling profiler, does not require any instrumentation of the code, but for map, you do want to get symbols, so add a -G so you can correlate time in your run with source code. And it uses a sampler where we start out at the order of 50 hertz and gather data for about 30 or 40 various metrics. And as we progress in time, we resample the data on a new time base and then decrease the sampling frequency. And so for very long runs, whether it's tens of minutes or 10 hours, the amount of data per node remains relatively constant, at like well under 100 megabytes. So at the end of a long run, it's relatively easy to aggregate the data up to the login node and create a single output file for analysis in the user interface. Now, a couple caveats of that is a lot of time in codes, you might not want to look at an initial phase or a finalization phase. A lot of times there's like some I/O setup and some I/O teardown, so to speak. There is the capability of, you can say, don't start sampling until after time X, and then stop sampling after time Y. So for a lot of performance, you're probably going to be focused on the core computation phase of your application. And so there's ways to kind of cut out that startup and tail end these. One other comment on the overhead is, as I mentioned, it's relatively low at the order of 5%, but that is mainly during the sampling phase. So as you start up and you're running, the overhead on the application is typically well under 5%, but it does require some time at the end of your application to aggregate the data from each node. So our tool starts a daemon on each compute node that's gathering the data, doing the statistical sampling, and at the end of your execution, those are kind of aggregated up the tree to a single file on the login node. And that part, depending on the size of your run and the nature of your sampling, can take a little while. So when you're first getting started, if your run typically takes, say, 58 minutes, and you usually give it an hour on the first tries, you might want to give it a little bit more time until you get a feel for how long the aggregation phase in map takes. Python. So relative recent history, we've added support for both profiling and debugging in Python. We're seeing a lot of uptick with this in the States. Historically, I've primarily supported our customers in the States, and especially in our government labs, there's a lot of uptake with usage of Python, and so it's exciting to see this grow. Especially a lot of other disciplines, seeing people in disciplines outside of the quote core hard science type of things that are getting access to HPC resources. Python makes the quantitative aspects a lot simpler. One thing I want to kind of note with it is there's obviously a lot of Python usage for various purposes in an HPC center. Our tools were primarily focused, once again, on HPC, SPMD style programs. So something that might use MPI for Pi or some other SPMD oriented tool. is our focus for Python. Just a couple things I've had in the last couple of years to highlight is kind of working from home things. In particular, is a remote client. This is kind of always the preferred setup, but it's even more important now, where folks are working at home a little bit more, is the preferred working mode is you install a client on your desktop, and we have clients for Windows, Macintosh, and Linux, and then you remote connect to your cluster, and it creates an SSH tunnel to communicate back and forth. So much more responsive because it's just moving a little bit of data back and forth. Then once connected, you log into your cluster, go into your existing submission script, and prefix the existing MPI run with MPI run, app run, however your site is configured. And that's all described for your specific setup at Archer on your web pages. And just a little bit of follow-up material for looking at things in a little bit more depth, if that's of interest, and I'll be sharing the slides afterwards. Okay, so let's start with performance reports. As I kind of mentioned in the performance roadmap methodology, I think the best starting point for getting a high-level view is a performance report. And this is useful for both developers and non-developers. So for example, system administrator type folks that want to see that the machine is being well used, it's easy to create a performance report and see that the configuration is good. And in fact, one usage we have is we usually participate in the student cluster competition at SC, and kind of the tool of choice for that is performance reports, and that the student's goal usually is to take a well-established code like war for lamps or something like that and tweak the knobs of how they deploy it and build it. And performance reports is a really powerful way to do that, and it doesn't require a lot of understanding of the code. So okay, so I'm just running in my own desktop machine here, so I just want to kind of correct the workflow, so to speak. Is the preferred workflow at your site on your setup is going to be start up the clients, connect to the machine, as described with your site-specific stuff, then log into the login node and edit your existing submission script and prefix the existing MPI run. So you'll probably have an MPI run with a bunch of arguments for your application. Just prefix that run with perf report and the application. And this will just run as usual in your batch system, generating a .out, .error type of file, depending on how your system works. And then in addition, by default, performance report will create an HTML file. And for the summary view, that's a really nice approach. You can also create a CSV file. So for some other use cases of making it part of your regression testing. So in States, we have a lot of sites that will create a CSV file performance report that they include with the check-in for a given code version. So if you find that you do introduce a bug or a problem, you can actually roll back in your source code control, and not only the source code, but you can get a performance report of what the performance was and compare it to the new phase where there's a problem. It also enables a little more automation of using tools like sed, grep, Perl, etc., to do some comparison of performance across different versions or iterations of your program. Okay. not the friendliest name to type. Maybe cut and paste, be a little friendlier. And you can also specify a name if you want. If you don't specify anything, it gives you this rather verbose automated name. Okay, so let's kind of go through the interface here at the top. It has some information about the run, what the parameters were, the machine that was on, historical information, and then this little chart where visually you can kind of get this pretty quick view of how things are working. Now, obviously, we typically want this chart to be biased towards compute as much as possible. In our case, we have some bias towards MPI. And looking at the high level, we see that there's only 54% of time being spent in compute. Typically not very good for an HPC code. Point being is, once again, thinking of the performance roadmap, it at least gives us an initial flag to investigate. So we're seeing that like over 45% of time is being spent in MPI. And if we want to understand that a little bit better, we can look at the lower level. So what I like to do is kind of do in reverse order of eliminate things that don't appear to be an issue. So this code does very little I/O, so that's not an issue, kind of eliminate that. And then the next step would be like looking at MPI. That's quite a bit of time in collectives. Actually, that's a really high amount of time for a typical HPC code. So that's definitely something of interest. So at this point, without knowing anything about the code at all, we kind of have an action plan of MPI is a potential issue, and that we want to understand that a little better at what's going on. So it might be a configuration issue. So what first step might be to look at how the code was deployed. It might have been a case of way too many nodes were used for the amount of compute per node. I know in my case that was not the amount. I'm just using one node, so to speak, a very small amount. So the next step then would be to bring it up in map and look at the source code and see if we can isolate in the source code what is going on, what the problem might be. Okay, so once again, the workflow is the same as it was for performance report. Modify your submission script prefix it with map. So prefix the existing run with map -- profile. Now, you can use the user interface in map to sample your program. I kind of discourage that for most use cases because you essentially have your submission locked up, and the data is really not useful until the data are done. So I kind of prefer the workflow of you go in, you run map kind of offline, so to speak. You say -- profile, which means gather the data, do the profile, but do not bring up the user interface. Just create the output. You'll get a notification from your system. Once again, .out, .air files, and then also a .map data file for map. And then go back to the client on your desktop, browse to the cluster, and bring up the file. So you can use the interface. For most all situations, I recommend against that. Okay, so we submit the job. Once again, it's going to run as it usually would on your system, creating the usual output. This is a pretty quick run here. It'll just take tens of seconds, I believe. Okay, so then bring up your client. I'm just going to run directly here and open the file that it generated. So once again, this is an aggregation for each node. I only had one node, and there's one daemon on each node that gathers the data, does the statistical sampling, and creates this one file. And it's actually just a compressed XML file. So you can actually uncompress it, get the XML, and there's some interesting post-processing cases that you can use with that. We have sites in states that'll use that in regression type testing things, where we're comparing different metrics across different views. So let me go through the user interface at top. First, at the top, we have various charts where the horizontal axis is the timeline of the run. For my case here, it was 9 seconds, which, by the way, is really not enough. For a toy code like this, it's okay. But because of the way that the statistics in our sampler works, it's really best if you can have your run at least for several minutes, ideally even tens of minutes. Is best, and arguably when you're running at a realistic scale for your code, you're probably going to get more representative data when you do that. So it's kind of a short run, but for my toy code, it's accurate enough. So we have 9 seconds in the horizontal timeline. In the vertical, we have the quantity of the metric. Now the top chart is a little different. It shows the quantity for about 8 different metrics. Shows time spent in I/O in orange, and I believe there's just a little teeny slice of that over to the right, so we can pass milepost 1 on the roadmap. Quite a bit of time so time in MPI is in blue, quite a bit there, and from the performance report, we were expecting that, but now we're just getting a little more insights on the details of that. Time spent in single thread compute is in green. I am not using OpenMP in this program, so there's no multi-thread compute. That would be in a light green. GPU would be in purple. Luster would be in beige, and I think that's about it. But about 8 metrics, and the point being is a very quick way at a high level to get a sense for what the program is doing. So for example, picking up a new code where you don't really understand the internal functionality yet, this is really a quick way to see that is in the activity diagram at the top. Now below that, various charts. This is just the default, but there's about 30 various metrics that we gather, and we'll go through some of those. And within the metric chart, we display the mean, the maximum, and the minimum as a solid line. And the shading around the mean is kind of the variance across all of the processes, where the intensity of the color is the magnitude of the value. And this is really at the heart of the scalability in maps. So I can run this program on hundreds or thousands of processes, and the shapes of the curve are going to vary a little bit, but the appearance is going to be very similar. Now, if we hover over the chart, we can get kind of an instantaneous value. So let's go to like 1 second or so. So at about 1 second in, we can see the floating point ranged from 80% to 100%, with a mean of 90% and standard deviation of 10. That's not too bad, but if we continue on to about 1.5 seconds, we can see that it ranges from 0 to 80%. So that might not be really good. So that might become something to investigate. But once again, we want to kind of fix problems in the order of potential magnitude. So over on the right here, we got this active menu for cycling through presets. When I'm first starting with a new code, I kind of like cycling through with this just to see kind of at a high level what's going on. So there's a few CPU related things going there. Preset CPU time. Typically this is only relevant on clusters that don't have dedicated compute nodes, but sometimes it also can help you spot threading issues where there's thread contention. I/O, once again, we aren't hardly doing any I/O, so not much of an issue there, but kind of get a high level picture. Memory. Now I mentioned memory. It's a way of like seeing jumps in usage. So in memory usage here at about 5 seconds in, we see a jump in memory. That might be the nature of the algorithm, or that might be a memory problem. and MPI. So in the MPI call duration, there's definitely something going on here. So if we hover over the first kind of sawtooth pattern in MPI call duration, look underneath the charts, we can see that it ranged from 0 seconds on rank 3 to 600 milliseconds on rank 0. So that's really terrible. So there's at least one rank spending significant amount of time not doing any work. Now with MPI, you typically want to see these kind of spiky patterns where most SPMD architectures will have a code where one part is doing a whole bunch of work, it gets to kind of a boundary halo exchange, exchanges data with neighbors, and it gets back to work with a minimal amount of time not doing compute. Obviously, you want the bulk of the runtime with the nodes doing compute. So definitely an issue with MPI there. So let's go back to the default, and we can add in individual items. I'm going to add in that MPI call duration to the charts. So the core of the workflow at MAP really is using these charts to see potential problems and then isolate in the source code the area that represents that problem. So let me show how the source code view by default shows a little activity plot next to each line of code showing how the time is spent on that line. So on line 10, we're running about 39% in that imbalance function. Hovering over that, we can see that it's broken up into a single thread compute and MPI. On line 10, we're running about 17% of the entire run, and it's all in single thread compute. And kind of in the last phase or the last function call of this, it's kind of split between compute and MPI. So we want to look at this pattern first. So we highlight that section of the chart. MAP will make a couple updates. It updates the quantities to the left of the charts to only show information for my selected area. And then most importantly, it updates the source code to only show the activity charts for my highlighted section. So we can see at this point 100% of the time that I selected is in this imbalance function. So the workflow to isolate that is we go to view, fold all, so essentially collapse all of the code blocks in the source code. And then block by block, we'll drill down in the source code to isolate the issue. And as we do that, we also display an additional pane to the right. It gives some a breakdown of how time is spent and what instructions are being done. Since this is an MPI problem, it's not really as interesting for instructions, but when we move to a CPU related problem, that can be more interesting to help isolate that. All right, so we're about 3 or 4 blocks in at this point, and we've isolated essentially to these 2 lines of code. There's a line on 85 that is doing this computation here, and a line on 88 that is doing a reduction. And so there's a couple steps here. One thing I like to do, like in an actual tutorial, is have like half the students immediately go to the debugger and use the debugger as an analysis tool to try to understand what's going on. And then the rest of folks just read the source code and figure it out. And even with this rather toy code size problem, folks that use the debugger almost exceptionally find the problem quicker of what the issue is. So in my case here, the punchline is it's iterating over a rank number, so it's not distributing the work across all the processes. So really kind of the point in that exercise, which I think is really useful. Like so many HPC codes are daunting, and a high percentage of people kind of going into HPC are in roles where you're picking up a code and you've been tasked with modifying the code to do some additional type of work. Kind of one of my core experience was taking the WRF code and doing adjoint coding of part of it. And When I did it, it was just try to understand the code and just directly, and using the debugger. I think when you're in a role of needing to understand the code and then start making some changes to add or modify functionality, the debugger is a great tool to help the kind of understanding process as you're doing performance optimizations in that kind of role. Make use of the debugger also to help you in the process, and of course to make sure that things are correct. Kind of step zero, so to speak, on the milestone. So that's the heart of the workflow in MAP. Now there are kind of what I view as kind of bottom-up techniques, kind of more of the gprof style, where you want to see time spent in a function and in the children of a function. And that definitely has utility of where if you narrow down a problem to say, you have my FFT, and my FFT and its children are the source of your performance issues at the given moment, using this type of bottom-up technique is useful. But in terms of methodology, often in that case, what you've done is you've isolated it in a SBMD context, and when you want to go to isolate and work on just my FFT, you can do that in a single process, single thread context, and then move back to an HPC context. Also for threading, some of the similar view, and also using the activity diagrams of a breakdown of how time spent is in kind of a stack view. So that was a MPI related problem. Let's go through the same workflow, but focus on a compute problem, on a CPU problem, and see how it looks. So let's go back to the defaults. So once again, kind of go through, get a sense of branching is not an issue. Now, one to point out on integers, it sometimes gets overlooked, is even though your code, an HPC code, typically won't have many integer operations, looping and branching and jumping are integer operations. It's done differently in different architectures. So don't be surprised if you see a fair amount of integer computation in what you think is a fully floating point code. So I'm just looking let's maybe have a look at this vectorization. So let's highlight a section of vectorization. And I'm going to find one that's a little bit. Okay, so yeah, let's start with this section where it's a lot of low floating points operations. And then once again, we'll go to collapse all the code blocks, drill down block by block, and even without going into the elements here, we're seeing that it's essentially on these two blocks. And this is an issue of, so it's obviously in Fortran, and accessing a Fortran variable in row major order instead of column major. So C is orders data in row major, Fortran in column major. So when you do that, it gets cache misses. It has to reload cache on every single step. The cost of loading at each step is more expensive. Now, this might be a case of, kind of somewhat of the experts understands the issues with row major versus column major and Fortran versus C. Maybe everyone doesn't. This is a case where it's really useful to use the output report, the vectorization reports from the compiler. Intel in particular does a great job and it provides a ton of information, but if you turn that on and just head right into the output, wading through it to try to understand what's going on, most of the issues that it highlights are probably not going to be performance problems. But if you've isolated it down to these blocks of code, you can go back to your compiler, get the vectorization report, and go directly to this this area, and it will give you some insights of why it's doing that. Okay, I think I'm gonna move to a different code just to show what OpenMP looks and feels like, and see what it looks like with C. I think I have that in C, not Fortran. Okay, so I'm just going to use a file that I previously generated. So once again, bringing up the client on my desktop. And this would be the way to connect with that. So here's a machine I was using recently. And then once you're connected, select load profile data. Browse. Browse to the file of interest, and I'll load it up. So once again, first thing to look at is the activity diagram. So in this case, it's almost all in light green. So this code is probably about as optimal as we're going to get it. And the entire compute is within OpenMP, and we can also see that as we hover over it, and then just a tiny amount of MPI at the end. And I've actually played with this. It was a public code of it's using two processes, two OpenMP threads, and so obviously there's a little bit of communication at the end. Then we can also look in the source code view and find where pretty much the entire compute is done within this OpenMP pragma. So not much opportunity for performance improvements there, but I just kind of wanted to highlight of how it looks in OpenMP and in realistic hybrid codes where you're running a lot of threads per process. This really becomes important of using the OpenMP capabilities to see that you're getting a good balance across it. And then one kind of plus with OpenMP is, at least in my opinion, it's relatively easy to get work balance in an OpenMP pragma relative to how it's done in MPI sometimes. Okay, so Fortran example, C example. Let me just kind of show a Python example. As I mentioned, this is really growing quickly in the States. I work with the NERSC lab, Berkeley, a lot, and 3 years ago they were using about a third of their folks were using Python, and now it's like 2/3, and most early career folks coming in and new research, especially in non-hardcore sciences, are using Python. It's exciting to see that growth. So once again, I'm just going to use a result that we previously sampled. So it's giving me a warning here that I did not get very many samples. In a realistic code, that would be a little more concern. In a toy code like this, it didn't run for much time. It doesn't matter too much. So let's look at the activity diagram again. So very similar to what we had, but for example, if we hover over at about 10% in, we now see below the charts a section that's showing time spent within Python. So at this time phase, it's 50% in compute and 50% within Python. So once again, a really quick way to see high-level issues. Now, time spent within Python is not an issue per se, but the most typical kind of architecture with a Python-focused HPC code is you're going to have Python driving the code, something like an MPI for Pi, but underneath you're going to be using NumPy or your own compiled code. And the core thing you want to be looking for is that there's minimal amount of time spent within Python and that the bulk of the compute is within your compiled code. And often that might involve restructuring how you make calls and things like that. And in the endnotes of the slides that I shared, a colleague did a webinar that walks through several phases of a linear algebra oriented application of doing it in Python to using some open source to using MKL and showing how you can get to like virtually no time is spent within the Python execution, but yet your code is much easier to read and write and those type of issues by using Python at the high level, somewhat non-computation phase. So just checking my notes here, but I think that's the bulk of what I had to show. So I think so. So any questions?
Feel free to speak up if you have a question, if that saves a bit of time on typing.
So also I just wanted to highlight, I think I mentioned in our discussions with debugging last week, is I'm somewhat new supporting our sales guys in Europe, but kind of core part of my role is to help with using our tools. So if you have usage issues of like how to work with your code or how to get things going, obviously you have a lot of expertise at your site, but I'm also a resource for that, and I encourage end users and your administrators to take advantage of that.
Okay.
And also the follow-up material. There was a few in that of things that were a little bit long to kind of do in an interactive session, but I referenced a few blogs that go into a little more detail on performance engineering.
Right, so we have a question. How does map, I guess, deal with skew?
I'm sorry, deal with what?
Do you want to elaborate? I'm afraid I'm not familiar with this.
Yeah, I'm not sure I understand that.
So how map deals with knowing that the same time is on all the processors or on all the processes?
Oh, okay. Yeah, no. So that's a good question, and kind of start describing perhaps just a little more about the kind of sampling technique. So once again, there's a process on each compute node that is doing the sampling, and it interrupts on a clock. And the clocks on most cluster across the node are quite accurate relative to our 50 hertz sampling. So we sample at the order of 50 hertz. We start out at that sampling, and the clock accuracy on the compute nodes is relatively accurate, such that that sample for each process on each compute node is pretty much at the same time. It's statistically kind of close enough, so to speak, at a 50 hertz sampling rate. So when you aggregate them together and you get the plot, this is somewhat of a statistically sampling problem. They won't be exact, but numerically they're going to be quite close to each other across the processes. And since it's given in a visual way, it'll appear pretty consistent. Now, that said, there is the ability to set the sampling frequency. We somewhat discourage that in that, as I mentioned, one of the strengths is the nature of our algorithm makes it very hard to overrun your system. And when you increase the sampling frequency, there's a couple overheads that start to cause problems. As you might start creating a lot of data and overwhelm the system, but almost more importantly is the overhead of the sampling process itself is going to bias the output of it. So it's the low overhead is not just so your application will run as much time, but if you have high overhead, and this is also true in an instrumentation technique, is if you have high overhead, it's going to start biasing what the actual output of a profile looks like. So yeah, I didn't mention being able to change the sampling frequency, but that is a potential. But what I encourage is, in most cases, everyone's always skeptical. I was skeptical myself of like 50 hertz seems awfully slow, but for an HPC application where there's often some startup, some tear down, and then a core part of it is going to be iterative methods doing numerical stuff, is the sampling technique gives very accurate results of the actual profile. And our development has done a lot of research and of comparing this with richly instrumented runs and kind of verifying those statistics. But that said, it's often the case where you might nail it down to quote it's my FFT that's having a problem, and you want to get some very fine resolution within that. What I would encourage is, go to the one process situation where you're profiling my FFT, looking at its children at a relatively short run, not a lot of processes, just one typically you can run it at and get the detail.
Okay, great, thanks. Are there any other questions? Okay, so we have another question. Can you elaborate on profiling jobs with a lot of I/O and how this can be optimized?
Yeah, so if you're profiling for I/O, you're probably profiling a given phase, like a startup or set down phase. So I would definitely use the start at and end at function. So you're just looking at I/O. So you'll just exclude that part and not mix in the computation versus the other way around that I kind of described. So starting with that, and then in I/O, kind of the first things, start with the performance report, and it'll like highlight if there's blocking issues. So look for blocking issues, seeing that you're getting balance. So a lot of HPC codes are, I think a lot of times I/O to get workload and balance and being able to use all the resources using something like HDF or something where you could have distributed I/O on your file system, whether it's Lustre, GPFS, or some type of distributed file system, is using a I/O system that can take advantage of that. If you're doing raw I/O onto a file system, so like one I have experience with is in Wharf, it'll do raw I/O into the system, and it's easy to have certain processes holding up others because they have more than their share of what they're outputting for processes. Now that's not saying it can't be done. You definitely can balance that, but it's a little bit more of a balancing challenge. Now in terms of I/O, I think I showed it. So we have kind of the raw I/O numbers that can help see that, and just as we saw with MPI or CPU related things, we can see how the distribution is being done across the processes. Not much I/O in this process, not too much interest, and I'm not sure. And if you happen to have a Lustre system, we also support that. I don't have Lustre on here, so I don't have those metrics available, obviously, but we'd have it for a Lustre setup also. So one item I think I overlooked, and I apologize, I don't know your site very well, is CUDA support. So we talked a little bit about CUDA support in DDT last week. We also support CUDA in MAP. The workflow for finding problems in CUDA is entirely the same. So the activity diagram would show time spent in CUDA in purple, and then the CUDA metrics that we support are the 4 that I have here on the menu, and those would come up as other metrics that we could dig into, just as we did with MPI and floating point vectorization. This data file does not have any of that. A couple things to kind of watch. A little bit of an issue with CUDA is you can profile at a line level within CUDA kernels, but the overhead of that is quite high compared to a host. So in terms of methodology, what I recommend is use NVIDIA's Insight tools on a single node mode to start out with your CUDA code. And they also have the overhead also. I mean, we're just using their stuff underneath in a multiprocess mode. It's when you're profiling it at a line level, there's inherently a lot of overhead in that. But if you start at a single node level with Insights, kind of do your best job to see that the kernels are optimized. And then where MAP really adds value is to see that when you're running on a multi-node setup, you're getting good balance of GPU workload across the various nodes and across the various cards.
So related to this, are there any plans to add support for AMD GPUs?
We actually have support for the Oak Ridge AMD GPUs. It's still kind of in a pre-release stage in that some of the infrastructure to make that completely work is in AMD's court. So our stuff is not completely working because theirs is not completely available. I think the timelines are such that they're due to be production by the end of the year, and AMD thinks, and we think it's all going to work. And I played around with some of the pre-release, and it's pretty cool in that it all looks and feels the same as CUDA. And I'm kind of new to the HIP language environment, but even their language is pretty similar. So in our tools, it all looks and feels and works the same. Now, in terms of business-wise, we're kind of in a mode of we did that work for Oak Ridge under NRE, and we're supporting them on it. Whether we are going to officially make it a product for general release, I think the business people are waiting to see how that progresses in the market. So obviously, doing it for one customer and making it work is a little different than making it a robust commercial product.
Okay, great, thanks. I guess if there are no other questions, then we can wrap it up. So thank you, Beau, once again for both weeks. I think they were very informative and definitely very useful, and look forward to using it during my work. Thanks.
Great, thank you. Yeah, appreciate the chance to share our stuff.